Okay, I'm going to spend about 5 minutes talking about inference and optimization in all-pay auctions. This is a topic area I think is really important. I think one thing that computer scientists working in algorithmic mechanism design could really be helping in offering in the science of mechanism design is how to use the data that's collected in these mechanisms to make the mechanisms better. Okay, and typically you don't get a chance to redesign a brand new mechanism from scratch, which is what a lot of us do in our theory papers. Typically someone's got a mechanism and they want to know how to tune the parameters of that mechanism from the data they've collected. So I'd like to sort of look at that kind of a question. And this is really relevant today in these online marketplaces like Zillow or Uber or Google ad auctions or Booking.com, etc. These kinds of questions. So I'm going to switch gears and talk about sponsored search a little bit, but you can connect it right on to the all-pay position auction if you and translate that yourself. Okay, so here's a motivating question in search engine advertising. So if you do a search on Google for search advertising, you'll see these ads in the main line, ads in the sidebar, and here's an interesting thing. The search for search advertising turns up one mainline ad and a bunch of sidebar ads. A search for search engine marketing, which is basically the same thing, turns up 3 mainline ads. So here's a question for auction design. Which is better for this basically the same search? Having 1 mainline ad or having 3 mainline ads? Okay? So if you were Google, you might turn to something like A/B testing, which is the industry speak for randomized controlled trials, to try to determine whether A, 1 mainline ad, or B, 3 mainline ads gave them more revenue. That's actually going to be a little bit problematic, and I'm going to explain why right now. So if we were to randomize traffic into A and B and compare performance, that'd be the standard framework for A/B tests. This is randomizing the user traffic. So if we were trying to estimate the click-through rates of the ads, this would be actually really good because the user searches, we randomize A or B, and then we observe their behavior of what was their propensity to click on the first slot when we were only having 1 mainline ad versus their propensity to pick on the first slot when we had 3 mainline ads. That we can readily observe in this behavioral experiment. So what I actually care about is auction revenue. Remember, revenue connects back to the accuracy in peer grading, so I care about revenue. But the setting is a little bit different for revenue because the advertisers typically bid well in advance, and then a bunch of users show up and we randomize them A and B. And then after a month of user traffic, we report back to the advertiser what their payments are, how many users clicked, etc. Okay, and if the advertiser's bidding in equilibrium for the mechanism I'm running, they're actually not bidding in either A or B. They're bidding in a mechanism which mixes 50-50 between A and B. So that's a different equilibrium from the equilibrium I care about. Okay, so here's what it might look like with 3 mainline ads. Here's what it might look like for 1 mainline ad in terms of the position weights. And if you 50-50 mix, you get the average between the two. So the advertisers are really bidding in this auction, the gray dashed line. Okay, so just to look at a toy example, if we did 3 bidders, highest bid wins with 1 unit or 2 units, it looks like this, and the 50-50 mix looks like this. So this is a much simpler, it's a stylized version of the last slide. Good, and here's the interesting thing. I did this with a bunch of simulated data for equilibrium, where I randomized the auction A or B every time, and I looked at my bids, and the revenue, of course, if it's A, is just the highest bid wins. If it's and pays their bid. If it's B, it's the highest 2 bid wins, so we sum the 2 bids to get our revenue. Right? That's the equilibrium bids we have. So you could try to do a back of the envelope calculation where you say, well, if I want to compare A versus B, let's just look at the times I ran A and calculate that revenue, and look at the times I ran B and calculate that revenue, and see which one's bigger. So you can do that, and you'll observe these according to the numbers. So I put in zeros where it was not that auction. Okay, and I summed them up and averaged. Okay, so it looks like B is better. But remember, the bidders bid before they know whether you're doing A or B. So these bids are going to be the same regardless of whether you did A or B. And B sums the top two numbers, and A sums the top one number. So B is always going to be bigger than A. So we have zero signal in this data, the data we collected here, right? And what horrifies me is that this is actually pretty close to what people in the industry like to do here. And that makes me very, very nervous. So this improper A/B test always shows that A is worse than B. If you actually look at this bid data, back out what the equilibrium was, and then solve for what would have happened had you actually just run A or just run B, which I can do because this is synthetic data anyway, right? You'll see that actually these auctions get the exact same revenue in the auction I got. That's just, up to some noise. Okay, so there's a missing effect that if I sell more units, there's less competition and bids should be smaller. So bids should be lower in auction B than they were in auction A, and we're not seeing that here. Okay, so my big question was, how can I do things like A/B testing, or if I run one auction, estimate the revenue of another auction from data in the auction that I ran? That's my question. Coming back to peer review, given the data for how the peers are performing in accuracy to the TA, how do I adjust the position weights so that I optimize my learning objectives or accuracy or whatever I care about? Okay, so here are the results from this work. There's a revenue estimator that takes bids in A and B and directly calculates the bids in auction C, some auction you didn't run. This revenue estimator is just a weighted order statistic. What does that mean? Collect a bunch of bids. Given the auctions you ran, the auction you want to estimate, I'll tell you some coefficients. You take those bids, you sort them, you multiply these coefficients and add them up. That's what your estimator looks like. Super simple estimator. Okay, the error of this estimator looks like this, where capital N is the number of samples you had from the bid distribution, little n is the number of bidders in the auction, and epsilon is the probability that you ran B. Okay, so you can run B with very small probability because it appears in the log. What I think is interesting is that our dependence on epsilon, the probability you run B, is way better than ideal A/B testing. If I did ideal A/B testing, the number of bids I have in B is epsilon n, because epsilon fraction of the time I run B. So I have epsilon n bids in B, so my error should be something like 1 over square root epsilon n, which depends polynomially on epsilon versus logarithmically on 1 over epsilon. So we have a much better dependence on epsilon. Why is this? This is because in our auction, every bid responds a little bit to B, and we can learn from that, whereas in the ideal A/B test, only the bids in B respond to B. So if you're running with a very low probability epsilon, we rarely see bids in B. Okay, this is a result I really like. There's a universal B test, meaning if I want to just be able to estimate the revenues of any auction in the future, there's one auction B I can mix in that allows me to get good data that I can always estimate auction revenues from in the future of other auctions. Okay, and given the data we get back, we can optimize revenue for all feasible position auctions. Okay, that's my results overview. I want to give you one more slide on sort of the basics of econometric inference on how this works. Okay, I'm going to skip this. So the basic idea behind how you do inference with bid data, which is what is the big change here over sort of the classic models of machine learning and statistics, is starting with the following assumption. I assume that bidders are happy with their bids. What does that mean? A bidder's bid is the best bid given the distribution of other bidders' bids. Okay? However, the other bidders' bids are observed in the data. We see what other bidders bid. So we know what bidders are best responding to. Given the optimal bid, according to the distribution of bids, I just need to then invert what was the value that made the bidder bid that way. And once I have the values, I could solve for the revenue of any auction I want. Okay, so that's the basic premise. So for the simulated data that I generated, my bids B1 and B2 look like this. So bidder 1 is looking at these bid distributions thinking, what should I do? We can calculate their allocation probability as a function of bidder 1's bid. It looks like this. And given that bid distribution, we solve for the bid strategy, invert the bidder strategy, et cetera, to get the bid, and then we can forward estimate revenue. Okay, so I want to stop there with that and not get into sort of the more details of how we derive our estimator. Thank you guys for your attention.
Since we're a little after 1, maybe we can take questions offline. Thank you for coming. Thank you, Jason.
Hey.
Nice talk.